Hi, welcome back. So in today's video, we're going to be looking at the interesting relationship basically between a function and its derivative. And so this is really just going to be based on the appearance of it, so like the graphs, not really like any formula. So here we have a question which says, consider the function f of x and approximately draw its derivative f prime of x. So this is just another version, like another way of saying derivative. And so what you might notice is here we have a curve, which is f of x, and we need to draw, basically, the derivative of this function. But the thing is, we don't have the actual equation, so we don't actually know how, like, we wouldn't be able to graph this. And so this is why this comes in handy to be able to like draw right away the derivative, and so that then you can see and notice some like relations between the two. So what we're first going to be starting with is we're going to start by observing basically what is happening with this curve. So first of all, we can observe that there are parts of it where the function is increasing. And we know that it is increasing because when you move along the x-axis, your y value is also increasing. And so this basically says that the part here, for example, this part here is increasing. But then here, you can see the x value still increases, but the y value decreases. So this part here is a decreasing part. Let me just annotate it actually. There, so this is increasing, this part is decreasing. And then we can do the same for the rest. So here as well, it's also increasing and then decreasing again. And you might see it will become useful because if you watched previous videos, you might have noticed that the derivative of a function is basically its slope at certain points. And so if we consider, for example, the slope at any points along this area right here, you can notice that the slope is going to be positive. And so this is already telling us an information about the derivative itself, saying that basically the derivative here will be positive, whereas here, because the function originally is decreasing, so the slope is negative. And so therefore your derivative within these, so from here and here, like these x values, between these 2 points, your function or like your derivative will be negative. And so on. So here, because it's increasing, derivative will be positive. And so this is why it's useful to observe this. And then there's something else that we can see is that between these increasing and decreasing parts, there is a certain point where it changes direction. And these would be basically called the maximum and the minimum. So here, right here, we have a maximum, and here we have a minimum. And we have another maximum right here. So let's label them, just so that we remember what we're looking at. So here we have 3 maximums and minimums total. And what you might notice here is that actually at exactly those points, our derivative will also have a certain like particularity at exactly those points, because you notice that there is a change from having a positive derivative because it's increasing to changing to a negative derivative because now it's decreasing after the point. So this point right here is actually very interesting because you can notice also if you draw, so here imagine this line right here is basically the slope at the maximum. So exactly at the maximum here we have a slope that is completely straight, which is 0 because there's no slope. It's not sloping up or down, it's just straight. So our slope is 0. And so what this is telling us basically is that at this maximum right here, our value of our derivative will be 0. So we can mark that here. So do you see the green point here? It basically means now that our derivative, when we draw it, it will reach a point where it has to pass 0. So when you're at exactly this x value, your y will be 0. And the same thing applies to the minimum right here. So if you draw the slope exactly at the maximum, it will also be 0. So you know that at this particular x value, you will again have an intersection. So basically your derivative will have to meet this point. And then we can do the same thing with our final point. This is a maximum here. And if we drew it, it would also look like this. So these are some other interesting points. So just because of this change from going from a positive derivative to negative derivative, it needs to cross 0. And what you might notice then is that if we divide up our y-axis into a positive region and the negative region right here, it basically means that at these 3 points, our derivative will have to pass through and change side. So for example, if it was on the positive side, after passing this point, it will go into the negative side because here it's decreasing, and so on. But we'll get back to it just now. Now I want to introduce to you first a different point, which might not be so obvious when you just look at the graph. So do you notice that this part right here increases and then decreases? So this is like, it looks like a bell curve, right? Which is a negative bell curve. But then if you look around this area right here, this looks more like a positive bell curve. And then again, here we can see another curve, but that's also negative. And let me just show you this little diagram here. So if our slope looks like this, a very easy way to remember whether it's positive or negative, you can see here this looks like a smiley face, which would look like that. So it would be like positive. So it's a happy person, positive curve. Whereas the ones that are sloping down like these are negative because they also look like a face that's not happy. So this is just a way to like remember the two. And so what you notice then is that we're going from having here a negative curve to a positive one and then again to a negative one. And so actually there is a transition point basically between each. So when you transition from having a negative one to a positive one, there is a certain point in the middle where it changes. So you're basically switching from one curve to another one. And so I can just mark it here, it's approximate. And then here again, we're changing from having a positive one to a negative one. So we can also label this. Oops. These are approximate points. Obviously, look at the question. It really says it's approximate. We don't have specific values, so it's like you basically do it the best you can. Okay, and these points actually have a name, and these are called inflection points. So these are really the points where you change from having a negative to a positive or positive to a negative curve. And okay, yeah, so I labeled them in this brownish color, so you can see them here. I forgot to put this in here, so these are the maximums and minimums in orange, just so that we don't lose track so far. Okay, so this is what we got so far. And now, let's consider, for example, this part right here, which is one of the increasing sections. So like I mentioned earlier, the increasing function here will lead to a positive derivative. And so I'm gonna mark it like this here. This is just for you to like make more sense of it. So you can see here, this rectangle here is placed in the positive region of the y, and so therefore we will find our derivative between these x values within this area right here. And then if we move on to this part here, so between this maximum and the inflection point that we showed earlier, you can see it's a decreasing function. And so therefore your derivative will be negative. Oh yeah, no, it also applies to here anyway. So this entire part here is a decreasing function. So our slope is negative, so our derivative will be in the negative region. So far we know our derivative will be here. We know it passes through this point. We know it's going to be in here, and we also know it's going to pass through this point. And then if we consider the area here, so between these two x values, our function is also increasing. So it's going to be positive again. So we're going to find it within this region, approximately. And then finally, from here up until the end, we notice the function is decreasing, so our derivative will be negative. And so we'll find it within this region. So these are very useful actually to already have quite a good guess of what the derivative is going to be looking like. Okay, but now just to make sure, because we don't actually know whether our, for example, within these x values here, we don't know if the derivative will be increasing, decreasing, so we're going to look at that right now. So for instance, let's take a point and let's put it right here. And then let's take another one and we'll put it right here. And now what we're going to do is we're going to look at the slope of both of them. So for example, this point here, the slope would approximately look like this. Yeah, it's really approximate, so it's going to be ish like this. But then if we want to draw the slope at this point right here, it would look like somewhat like this. And then obviously we have this one that's for the maximum points that is completely straight. And so what we're going to do is we're going to look at the slope of this point and this point. So I'm just going to take them. I'm not going to change them at all, but I'm going to put them side by side so you can notice a bit better. There. So these are the two slopes. This is from the bottom one, this is the top one. And you might notice actually that this one right here is steeper. So this one has a higher slope. The slope is of a higher number. Whereas this one, so for this point right here, the slope is also increasing, so it's the same direction, but this one is not as steep. So it has a lower value within the steepness. And so what this is basically telling us is that if we consider then the x value of this point and the x value of that point, but onto the derivative side, we know that at this x value right here, because the slope is higher, we will have a higher number. It will be a higher derivative. So at this x value will be higher up on the y. And we can just put some random number. So here you can tell it's there. It's at the same x value. And then the point that's here, because the slope is not as much, it will be lower than this one right here. And so therefore we can put a cross lower, somewhere lower. And this is where you notice this actually fits the rectangle that we put up a bit earlier. So now from this x value to this one, our derivative is actually going down. It's decreasing because the slope is getting less. As we're approaching the maximum, the slope is getting less steep. So therefore your derivative is also being less positive, so it's going down. Okay, So that's for this section right here. And then we know that when we get to the maximum here, because the slope is 0, we know it will meet the 0. So this actually fits so far what we've done, and it will go and transition into this area here. So what's going to happen in this area? So let's try and do the same thing again. Let's try to pick 2 points. This is very useful to notice the changes between 2 areas. So we have our 2 points. Let's put the slope for each of them. So this one would be approximately like this. And let's move it a bit. That's too much. So the slope here at that point, so before the inflection point, we have 2 points. And so this one you can observe the slope is of a certain value, but at this point you can see it goes steeper. So actually this value here is higher because this is a steeper slope compared to this one. So if we take at exactly this x value right here, let's just bring it down, and if we compare it to the second value, so this one, the one on top here, this one actually is lower. It's not as steep compared to this one. But we have to consider that because the overall curve here is decreasing, we're going to be in the negatives. So we're going to find them in here. And so this becomes a little bit tricky to think about because now this one is supposed to be lower than this one, but we're in the negatives. So a good way to consider it is this one is lower within the negatives. So it's a smaller negative. Do you realize how if this is our 0 here, where the x is, a point that is here approximately would be negative, but it would be quite low. For example, consider the number -2. Whereas if you compare it to a number that's here, let's say -10, it's also negative, but it's a higher negative. And so this is basically the relationship between the two. This one will be a lower negative, this one is a higher negative. So if we put those points up, you would see approximately something like this, where this one would be lower within the negatives and, well, higher, and this one would be a little bit lower like this, approximately. So this is so far for the first part, but now we've hit an inflection point. And what actually happens in an inflection point? So I'm going to go on to another slide. So let's go and look at this. So this right here would be an inflection point, because if we look back at this here, you might see that this part right here, if you follow my mouse, you can see it looks like a positive bell. Whereas after you pass a point around here, this looks, if you continue it, like a negative bell. And so, because we're transitioning between a positive one to a negative one, this point right in the middle here, we could call an inflection point. Let me put a cross at that point. It's going to be around here. And now what we're going to do is we're going to look at how the slope changes before and after our inflection point. So I'm just going to putting a few values, so we'll compare them between each other. So remember the one in the middle here, this is our inflection point. So let's look at this right here. So the slope of this one will be approximately, like that. And then the slope at this point right there will be steeper. And then we pass the point, and then we go on to the next one. So this one would be also quite steep. And then the final one, there we go. So this one actually would be not as steep as the previous one. So you notice how here the steepness goes, it's low, low, and then it gets higher, higher, higher. It passes the point, and then it's still high, but now it's starting to decrease, decrease, decrease. So we're basically increasing, and then after we pass the point, we're decreasing in our slopes. And so what this is telling us basically is that before the point, we're having an increasing, so something is increasing, but afterwards it's going to be decreasing. And so basically, let's go back to the other one. So what happens basically here at this inflection point is on our derivative, we have a maximum or a minimum. So let's do it with this example here. You can see the slope increases, increases, and then after the point itself, it slowly decreases again. Here we're just talking about the slope. And so exactly at the point, so at the x value of this inflection point, so along here, there will be a like a minimum. And so we can graph this, I think I have a color for that, yeah, here. So around there, right here, we have a minimum. Because now, if we consider the two points that are after the inflection point, so for example, this one and that one, if we consider them two, we would see that here the slope is quite steep. I'm not putting it right. Approximately there, and then the other one would be here, just not as steep as the other one. And so if we graph this, so here if we compare this point and this one is steeper, so it's higher in the negatives compared to this one who is not as steep. And so you would find a relationship approximately like this. Do you see what is happening? This is a little bit messy, but at this x value here, the derivative will be higher because the slope is higher compared to this point right here because the slope is lower. And so you can observe actually here the negative, the minimum. So exactly at the inflection point, we know there's going to be a minimum. Let's skip ahead a little bit and look at this inflection point. So because of what we just saw, we can just assume now and make the process a lot quicker. And because we know this is an inflection point, we know there's going to be a maximum or a minimum within this x value right here. And because of the way our graph is so far, because of this region that we already highlighted, we can tell it's going to be a maximum. And we can prove that by looking at the curve here. So you can see the slope here starts off quite lower, and then it increases. After this point, it slowly decreases and reaches 0. And so therefore, we're going to have a maximum here as well. So somewhere along the line here, just somewhere. We don't know where, so we can just put a random point. Somewhere along here, we're going to have a maximum again. So this is getting easier, isn't it? Okay, so far we have this, it's decreasing, we hit a minimum, we increase again, we hit a maximum, and so now we're going to decrease again. And we know we're going to hit this point right here, and then after this, we can see here, if we consider a point here, the slope will be of a certain value, but if we decrease and go a little bit farther down, the slope will be higher. And so therefore we can assume that after this, this point here, we're going to start decreasing again. And because we don't see how far this line goes, we can just assume it goes all the way down. Okay, so that's actually pretty much it. So now that we have all our points along the line, we can just trace a curve. So, okay, I did this one earlier. It might not match 100%. Alright, it's quite good. So you can see it first decreases, reaches a minimum, increases again, and re-decreases. Now let me show you on another slide the exact same thing, So like this, just without everything that we just did. So our red curve here, this is our original function. This is our derivative. And so now we can observe the relationship between the two. So that would be the end of the question. So just to review a little bit what we saw. So overall, when you have a function, you first find out which parts are increasing, which parts are decreasing, because then you know whether your derivative will be positive or negative. And then you find the inflection points, which you know will be maximums or minimums in your derivative. And then from there, you can just pick a few points with like along the line and just approximately put corresponding point of your derivative somewhere, and then you can just trace it. And this is how you find the derivative. So this was a very long video. I'm absolutely sorry, but hopefully you can understand it much better after this. And next time we'll be looking at some more examples, and hopefully we'll do it quicker and quicker. So yeah, thank you. Bye.